Hello everyone. Today I am going to read out the chapter Alkanes. The simple organic compound are hydrocarbons, the compounds containing only carbon and hydrogen. Depending upon the framework of carbon atom in their molecules, the hydrocarbons may have either open chain or ring structures. In addition, they may be saturated or unsaturated in character according to the nature of carbon-carbon bond in them. Due to these variations, hydrocarbons have been divided into different classes. We shall discuss the various classes of hydrocarbon one by one, starting with alkanes and cycloalkanes. Therefore, in this type of bonding, one atom completes its octet and acquires noble gas configuration by losing the electrons, and other by gaining the electrons. The atom which loses the electrons acquires a positive charge, and the other which gains the electrons acquire a negative charge. These two oppositely charged species come closer to electrostatic forces of attraction and form an ionic bond. Since electrostatic attraction leads to decrease of potential energy, and therefore the potential energy of the system becomes less than it was before the formation of the ionic compound. The electrostatic force of attraction, which holds the oppositely charged ions together, is known as ionic bond or electrovalent bond. The compound contains ionic or electrovalent bonds are called ionic compound. Formation of ionic bond. An ionic bond is formed when one or more electrons are completely transferred from one atom to another atom so that both the atoms acquire stable noble gas configuration. Let us illustrate the formation of ionic bond by considering the example of sodium chloride. Sodium atom 1s2, 2s2, 2p6, 3s1 has only one electron in the valence shell, and by losing this electron it can acquire stable electronic configuration of neon 1s2, 2s2, 2p6. On the other hand, chlorine atom 1s2, 2s2, 2p6, 3s2, 3p5 has 7 electrons in its valence shell and needs only one electron to complete its octet. Thus, both the atoms are complete octet if sodium atom gives one electron to chlorine atom. This tendency is responsible for bonding between sodium and chloride atoms. Therefore, sodium gives electron and become positively charged sodium ion, while chlorine take up electron and become negatively charged chlorine ion. These two ions are held together by electrostatic force of attraction, which constitute an ionic bond. The formation of ionic bond between sodium and chlorine may be illustrated by the following electron dot picture. When atom combine by electron transfer, the number of electron gained or lost must be equal so that the resulting compound on whole is electrically neutral. The number of electrons gained or lost by an atom in the formation of ionic bond is equal to its electrovalency. Atoms that readily lose electrons are said to be electropositive, while those which readily gain electrons are called electronegative. Let us consider another example of calcium chloride. Calcium Z is equal to 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 has two valence electrons and can acquire the configuration of argon by losing these two electrons. In the formation of calcium chloride, the two valence electrons of calcium are transferred to two chlorine atoms. Z is equal to 17, 3s2, 3p5, and all the ions thus formed have noble gas configurations. Schematically, the formation of CaCl2 may be represented as. Similarly, in the case of magnesium oxide, magnesium Z is equal to 12, 1s2, 2s2, 2p6, 3s2 has two electrons in the outermost shell, and oxygen Z is equal to 8, 1s2, 2s2, 2p4 has 6 electrons in the outermost shell. In the formation of magnesium oxide, both magnesium and oxygen attain the noble gas configurations by transfer of two electrons from magnesium to oxygen. The electrostatic force of attraction between Mg2 positive and O2 negative results in the formation of an ionic compound Mg2 positive O2 negative. Schematically, this may be represented as. In this compound, the electrovalency of magnesium and oxygen is plus 2 and minus 2 respectively. General characteristics of ionic solids. The ionic solids have the following characteristic properties. First, crystalline nature. In general, ionic compounds are crystalline in nature. X-ray studies of these compounds have shown that they do not exist in the molecular form but consist of ions of opposite charges arranged in some definite geometric pattern. Each ion in the crystal is surrounded by definite number of oppositely charged ions. Geometric arrangement of ions is different for different ionic substances. The mode of arrangement depend upon the size of the ion and also on the respective charges on them. For example, in sodium chloride crystal, each sodium ion is surrounded by 6 chloride ions. This arrangement is extended throughout the crystalline lattice. High melting and boiling points. In general, ionic compounds have high melting and boiling points and high heat of fusion and vaporization. It is because of the strong electrostatic forces of attraction between the oppositely charged ions. Consequently, a large amount of energy is required to overcome interionic attraction, which results in increased melting and boiling points. The variation in melting point in different ionic compounds are mainly due to first, charges on the ion, and second, ionic radii. The closer the ion in crystal, the larger will be the electrostatic forces of attraction, and consequently higher will be the melting point. For example, in case of sodium halides, the melting point decreases from NaF to NaI. As the size of the anions increases from fluorine to chlorine, the forces between the sodium and halide ion becomes weak and consequently melting point decreases as given. In case the interionic distance is almost the same between two compounds, the melting point is determined by charges of the ion. For example, NaCl and BeO have almost similar internuclear distances. The melting point of NaCl is 1073 Kelvin, while melting point of BeO is 2195 Kelvin. Higher melting point of BeO is due to strong interionic attraction between doubly charged Be2 positive and O2 negative ions in comparison to attraction between singly charged Na positive and Cl negative ions. Hardness. Ionic compounds are hard and rigid. The hardness of the ionic compound is due to the strong electrostatic forces of attraction between oppositely charged ions. Hardness of these compounds increase with decrease in interionic distances, and increase in ionic charges for crystals with similar structure. For example, LiCl and SRO have similar structure and their interionic distances are also the same. SRO is harder than LiCl because the higher charge of ion is SRO than in LiCl. Similarly, NaCl and CaS have similar structure and nearly same interionic distances, but CaS is harder than NaCl because of high charge on ions. On the other hand, all the alkaline earth metal oxides MgO, CaO, SrO, and BaO have similar structures and their ions are also doubly charged, but their interionic distance increases in the group from MgO to BaO. Due to increase in the interionic distance, their hardness decreases. Brittleness. Ionic compounds are usually brittle, that is, they can be easily broken into pieces on applying stress. An ionic crystal consists of closely packed ions of opposite charges. When enough force is applied to ionic crystals, one layer of ions move across the next layer. As a result, the ions of like charges come near to each other. This causes instability because of repulsion between similar ions and result into breakdown of the crystals. Fifth, solubility of ionic compounds. Ionic solids are generally soluble in water and other polar solvents having dielectric constants. Since water has a high dielectric constant, it decreases the electrostatic forces of attraction between the ions. As a result, the ions get separated from one another to give a solution. The ionic solids are generally soluble in water and other polar solvents having dielectric constants. Since water has a high dielectric constant, it decreases the electrostatic forces of attraction between the ions. As a result, the ions get separated from one another to give a water acts as dipole having negative and positive ends. When an ionic compound is dissolved in water, the positive end of the dipole interacts with the negative ion, while the negative ion of the dipole interacts with the positive ion. Due to these strong interactions between the ions and the solvent, large amount of energy is released. This is known as hydration energy. The hydration energy released is greater than the crystal energy which holds the ions. Consequently, the crystal lattice breaks and goes into the solution. Most of the organic solvents have low dielectric constant and are highly polar. Hence, ionic solids are only slightly soluble in organic solvents. Conduction of electricity. The ionic solids consists of iron. They do not conduct electricity. Conduction of electricity. The ionic solids consist of iron. They do not conduct electricity in solid state. The reason is that the anions and cations on account of electrostatic forces are held strongly at particular position in crystal lattice and are not free to move, hence no current flows. However, as the temperature is raised, there is increase in kinetic energy of the ions when the substances are heated to high temperature. so that they melt and the kinetic energy of the ions increases to such a large extent that they overcome the attractive forces and become mobile and are thus able to conduct electricity in the molten state. Similarly, when the ionic compounds are dissolved in water or some other solvent, the ions become free and therefore they conduct electricity in dissolved state also. Ionic reactions. Ionic compound split up into oppositely charged ions when dissolved in water. The chemical reaction of ionic compounds are characteristics of the constituent ions and are known as ionic reactions. Such reactions occur almost instantaneously. Non-directional character. The ionic bond is non-directional. In ionic compound, each ion is surrounded by oppositely charged ions held together by electrostatic forces. These forces are uniformly distributed all around the ion, that is, electric field is non-directional. Therefore, the ionic bond is non-directional. Close packing of identical solid pairs. Before discussing the structure of some ionic compounds, it is worthwhile to understand the packing of constituent particle, atom, ion or molecule in the crystal. In the formation of crystal, these particles get closely packed together. The closely packed arrangement is that in which maximum available space is occupied. The closer the packing, the greater is the stability of the crystal. In order to understand the packing of constituent particle of a crystal, let us consider the packing of hard spheres of equal size in three dimensions. If a number of spheres of equal size are put in a container and shaken, it is observed that they pack themselves in two common ways, as shown in figure. In arrangement, the spheres are packed in such a way that the row have horizontal as well as vertical alignment. In this arrangement, the spheres are found to form squares. The arrangement second. In arrangement second, the spheres are packed in such a way that spheres in every second row are placed in the depression between the spheres of the first row. In the third row, the spheres have vertical alignment with spheres in first row. A comparison of two arrangements of spheres show that in arrangement 1 the spheres are closely packed than in arrangement 2nd. It has been calculated that in the first arrangement only 52.4% of the available space is occupied by the sphere, remaining 47.6 of the space is empty and is called void volume. In the second arrangement, 60.4% of the space is filled and 39.6 of the percent of the space is empty. Thus, the arrangement second is more economical and it represents a close packing of spheres. It can be seen that in the closed pack arrangement, the center of three nearest spheres are at the corner of an equilateral triangle. Moreover, each sphere is in contact with six other similar spheres shown shaded. The number of nearest neighbor with which a given sphere is in contact is the coordination number. Thus, coordination number of each sphere in the closed packing arrangement is 6. Thus, the arrangement second represent closest packing of sphere in a layer. We can build other layer above the first layer to extend the packing in the three dimensions. Let us label the sphere in the first layer as A. It is clear from figure that there are two types of voids, hollow. In this second layer may be placed either on hollows which are marked A or on the set of hollows marked B. It may be noted that it is not possible to place spheres on both type of hollows. Thus, While building the second layer, only half the hollows are occupied and half the hollows remain unoccupied. Let us place the sphere on hollows marked B to make the second layer, which may be labeled as B layer. The second layer is indicated by dotted circles. When we come to packing of third layer, there are again two types of hollows available. One type of hollow marked A are the unoccupied hollows of the first layer. The other type of hollows are hollow in the second layer marked C. Thus, there are two alternatives to build the third layer as discussed below. The sphere of the third layer may be placed on the hollow of the second layer, that is marked C. On this arrangement, each sphere of third layer lies directly above those in the first layer. In other words, the third layer becomes identical to the first layer labeled A. This arrangement, if continued definitely in the same sequence, is represented as AB, 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 A. This type of packing is known as hexagonal closed packing and is abbreviated as HCP.